Welcome. This is Coach Dorf. Today we're going to talk about the derivative of trig functions. Before we do that, let's do a quick review of the product rule. The product rule says that if I have two functions that are both differentiable, f times g, and I take their derivative, we get f times the derivative of g plus g times the derivative of f. Why is that? Why do we get that rule? It's not intuitive that it should be that way. Well, let's look at this kind of in a geometric way. Last time I had talked about if we had a circle of radius r and its area then was pi r squared, its derivative of the area with respect to r equals 2 pi r by the power rule, and that's equal to the circumference of the circle. And we showed that geometrically by looking at the derivative as the rate of change. So if I was having my circle grow in area, that would mean that r would change from r to a value of like r plus h. And I have this new area on the outside of my circle. And as h gets smaller, that ring around the original circle, we get smaller and smaller, and that thin ring then would approach the circumference of the circle. So geometrically, we can think of that derivative of the area becomes the circumference because that ring gets smaller and smaller and approaches the circumference of the original circle. We'll use that type of geometric understanding to explore the product rule. So we're going to look at this geometrically and ask the question, why is the product rule? Why product rule the way it is? So how can I geometrically think of the product of two functions? Well, I can think of that as the area of a rectangle. If I make one side of a rectangle f and the other g, then the area of that rectangle equals the product, f times g, all right? And now, just like we did with the circle, we want to increase the area, increase the size of that rectangle by a little bit. So what we're going to be doing here now is we have our original rectangle, and now we're going to just increase it a little bit. It's going to look like this. So we have this new part here. And this is my original f, and I've increased the x value by h. So then this new area represents f of x plus h. And likewise, here's g. And now my new side length would be g of x plus h there, all right? And the derivative of the area of the original rectangle is the rate of change of the area of the rectangle. So we want to see what happens to this shaded part here. Maybe I'll use a different color. This shaded part in red, what happens to that as h gets smaller and smaller? All right. So what happens to the area of the shaded region as h goes to 0? Well, I'm going to think of this shaded region as really three parts. So I'm going to have this blue part, and I'm going to call that area 1. And then I'm going to have a green part here. I'm going to call that area 2. And I'm going to have this orange part, and I'm going to call that area 3. So first of all, area 2. Now, area 2 has a couple of h's involved. It has an h from f, and the f of x plus h, and it has the g of x plus h. So it has two parts of h's there. And as the green area gets smaller and smaller, it's going to dissolve into a point. And that's really not going to affect the total area of the shaded region as h goes to 0. So we can just say intuitively that this is going to go to 0 as we do that. What about the blue region? All right, so for a sub 1, we've got a rectangle, and it's going to be base. It's going to have f of x. So that's the base there. That's equal to this blue part here. All right, and we're going to have a height. And what is that height there? Well, that's a little bit harder to figure out. See, I'll draw that in purple. The height is going to be this purple part there. So the height is going to be the difference g of x plus h minus g of x, right? Because here's my g of x and here's my g of x plus h. And if I subtract those two, I'm going to get that purple region right there. And as h gets smaller, goes to 0, this becomes the same thing. This area then becomes the limit as h goes to 0 of g of x plus h minus g of x over x plus h minus x, which is just the derivative there. So as x goes as h goes to 0, that purple height there of that rectangle, the blue rectangle, becomes the derivative. So we can say as h goes to 0, the area of sub 1 is, which is the base times the height, is going to equal base, which was f, times its height, which is g prime. And likewise, if we look at area 3, as h goes to 0, the area of A3 is going to equal base of that rectangle times the height. That's going to be that orange, this orange shape here. And that is going to equal then the base. The base here is going to be prime times g of x. Just doing the same type of argument as we did for the area of A1. So then in summary there, as h goes to 0, the area of the shaded region, the total shaded region, that rectangle, is the area of A1 plus the area of A2, which is going to equal f of x, g prime of x, plus g of x, f prime of x. Well, what is that? That's the product rule. So just like what we had when we did the circle, we saw the rate of change of the circle when we were doing the area of the circle. We looked at its derivative, it's that rate of change, and we get that area around it. And then as x gets small, as h gets smaller and smaller, we get the circumference of the circle. We get the ring around the circle. In the case of the product rule, we have a rectangle. Then we have those three banded areas, the blue, the green, and the orange region or yellow region around it. And as h gets smaller and smaller, that turns out, those areas of the shaded region turns out to be the product rule. And that's a geometric, intuitive type of approach of why the product rule is true. Now, let's talk about today's idea, and that is the derivative of trig functions, right? So let's look at the graph of some trig functions here. So let's see, what's my graph of the sine function? So let's suppose I have the sine function here, and we'll do the graph in blue here, where we know it goes through the origin, and it is a wave shape that looks like this, and it repeats itself. And here I've got at the top, it's pi over 2. Here it's negative pi over 2. And it crosses here at pi and at negative pi. And then also here we have 3 pi over 2. And likewise, negative pi over 2, or negative 3 pi over 2. All right, so again, we can think of the derivative. Since we have a graph, we're going to think of the derivative as the slope of the tangent line. So let's draw some tangent lines in here. We talked about this earlier at the end of chapter 2. How can I sketch the graph of the derivative of function if I have the graph of the original function? Well, the easiest parts to do are when I have horizontal tangent lines. So I have those here. So the slope here is 0. And likewise, the slope here is 0. So that means if I'm going to draw in some values here on my graph. So this is going to be graph of the derivative, which we don't know what it is yet, unless you've had calculus before, but we're going to just assume that you haven't. So we're going to put in some values here, just like we did over on the left side. So we put in those values there. And what do we know? All right, so we said we had a horizontal tangent line here at pi over 2 and at negative pi over 2 for the sine function. So that means on the graph of the derivative, it should be 0 at pi over 2 and 0 at negative pi over 2. All right, and we can also see that we're going to have a horizontal tangent line here, negative 3 pi over 2, and at 3 pi over 2, all those are going to have 0. So we put in zeros there and there. All right, what happens in between those values? All right, so between negative pi over 2 and pi over 2, if I draw in some tangent line there, that slope is greater than 0. So that means in my graph of the derivative, the graph should be above the x-axis. Oops, let me redraw that. It should be above the x-axis, and it should connect the 2 points at negative pi over 2 and pi over 2. Likewise, in a similar fashion, we can do this between pi over 2 and 3 pi over 2. If I do a tangent line, that slope of that tangent line is negative. It's pointing down. So that means the graph on the derivative should be below the x-axis. All right. And likewise, if I do between 3 pi over 2 and pi over 2, it's also going to be negative there. So it should be below the x-axis. Well, so it looks like we've got a curve, again, a wave function, just like we did originally. And that looks like the cosine function. And that's true. And that's actually what happens. The derivative of sine equals cosine. Now, what we just demonstrated is not a proof of that fact, but it's just a geometric understanding of why it happens. Again, if we think of the derivative, because we have a curve there, we can think of the derivative as the slope of the tangent line, and we can use that then to get this result here, or at least intuitively think that would be correct. Now, the book gives a formal proof of this, which I'm not going to do, but you can look it up in the book, or you can go online and look it up. In a similar fashion, we can also show what's the derivative of cosine. And somewhat surprisingly, it's not sine, but it's going to be negative sine x. So we have a negative there. But those are two values that we should know, that the derivative of sine and the derivative of cosine are equal to those values there. All right, so let's do an example using those results here. All right, so we're going to say find the derivative of y prime, for y equals sine x over 1 plus cosine x. All right, I like this example because it involves not only the derivative of the trig functions, but it also involves the quotient rule. And you're going to have to use some important trig identity to simplify this as we go through this process. All right, so we'll start off y prime by the quotient last time. So this gives you a little bit of a review, which is a good thing to do. Let me just start a little bit lower here. So y prime is then going to equal, by the quotient rule, it's the denominator. All right, so I'm going to take this, the denominator, put it here, and then I have times the derivative of the numerator. So I put a derivative there. So there's my numerator, put it there. All right, minus the numerator, or the top, times the derivative of the bottom, or denominator. And then that's all over the denominator squared. All right, so there's the quotient rule. Now we'll simplify, or we'll take the derivatives using the material the ideas that we just did today, of the derivative of sine and the derivative of cosine. We're going to use those in here. So what do I have? I have the derivative of sine. And so we know the derivative of sine from above was cosine x minus sine x. And now I have the derivative of 1 plus cosine. Well, the derivative of 1 is 0. And then I have the derivative of cosine, which was negative sine x. Remember the negative sign there. That comes from up there. All right. And then we keep the denominator, 1 plus cosine x. Some people may say, should I multiply out that denominator? No need to do it right now. So let's just see where it takes us. All right, then I've got these multiplications here, so I'm going to distribute or share a cosine x times what's in the parentheses in front of it. And so I've got 1 times cosine x, which would be cosine x plus, and then I have a cosine times cosine, which would be cosine squared x. All right, and then over in the second part here, I've got now sine times minus sine, so that's going to give me a minus sine squared x. Oh, I wanted to do that in black. Let me just do that in black. So that's going to be minus sine squared x. And then all over the denominator squared, or what I have there. And so now simplifying this, I've got cosine x plus cosine squared x. And then I have my negative and negative, so that becomes a positive sine squared x over 1 plus cosine x, cosine quantity squared. And some people would say, well, I'm done. But here's where you remember one of the most important trig identities. What is cosine squared x plus sine squared x? Well, that equals 1. So we're going to put that in here, and we get cosine x plus 1 over 1 plus cosine x squared. And now some of you may say, oh, I'm already done now. But you're not, because what's in the numerator is the same thing that's what's in the denominator squared. So we have what's in the numerator is of course this, but that's the same as this. So we can reduce those out and get just 1 over 1 plus cosine x. And that's the final answer there for that one. Here, let's do another example. Sometimes I see these on homework or exams. What is the 101st derivative of equals sine x? Now, you may think I could just take the derivative 101 times, but let's look at this. So the first derivative is going to be, so the derivative of sine from what we talked about is before is cosine. The second derivative, I'm going to take the derivative of cosine and get minus sine. The third derivative is going to be, I have a negative sign, so the derivative of sine is cosine. I have a negative in front of it, so it's going to be a negative cosine. And the fourth derivative, which is often, instead of putting 4 tick marks there, we'll just put a 4 in parentheses. So we don't get confused that it's not the fourth power. If it was the fourth power, y to the fourth power, we'd have y with a 4 with no parentheses. But when we put those parentheses there, it means it's the fourth derivative. So now I have the derivative of negative cosine. Well, I know the derivative of cosine is negative sine, so I have negative sine. So that gives me positive sine. All right, now what happens when I do the fifth derivative? So I put that y with the parentheses 5. Well, I'm now going to have the derivative of sine. The derivative of sine is cosine. And notice here, there's a pattern. These are the same. If I keep going, let's do the sixth derivative. Oh, well, I've got the derivative of cosine, and it's the same thing as what I have above it. It's like this. So these are the same. The second derivative and the sixth derivative give me the same result. All right, if I do the seventh, derivative, I'm going to get negative cosine x, and that's the same as what is above it. So the third derivative and the seventh give me the same. And as you can see, if I do the eighth derivative, it's going to be the same as the fourth derivative. And I get this, I get that. So there's a pattern here, and it repeats itself every 4 derivatives. So when I do the 101st derivative, what do I get? Well, let's see, the 101st derivative, let me write it this way. Let's see. So y to the 101st derivative is going to be the same thing if I just keep reducing it by 4. So in other words, it's going to be reducing that, dividing 101 by 4 and looking at the remainder. Sorry, 101 by 4. So 101 then divided by 4 is the same thing as the first derivative. All right, because 101 equals 25 times 4 plus 1. And this part here is just going to keep giving me the same result over and over again because it repeats every 4. So this is going to tell me that the 101st derivative of sine x is going to be the same thing as the first derivative. All right, so the 101st derivative of y is going to be the same as the first derivative, which, if we go back above, was just cosine x. All right, so we have the derivatives of sine and cosine. What about some of the other trig functions? All right, well, what would be the derivative of tangent? Oops. Derivative of tangent. Well, what we can do is we can write that as the derivative of sine of x over cosine of x. And now we've got a quotient there, so we could do the quotient rule. So we use the quotient rule, and what do I get? I get the denominator times the derivative of the top minus the top sine x times the derivative of the denominator all over the denominator squared. All right, and so then I have cosine x, the derivative of sine is cosine, and then I've got minus sine x, and then the derivative of cosine is minus sine over what I have in the denominator. And so when I multiply those together, I get cosine squared x. And now I have, again, a minus and a minus there, so that becomes a plus sine squared x over cosine x squared, which is the same as cosine squared x. But then I use that trig identity again. This all equals 1 because cosine squared x, sine squared x plus sine squared equals 1. And I get 1 over cosine squared x, which is the same as 1 over cosine x, everything squared. And 1 over cosine is secant. So we get secant x. So the derivative of tangent, let me redo that. The derivative of tangent x equals secant squared x. All right, and likewise, we can figure out what these other ones are. Doing a similar approach, we could find the derivative of secant x because it's 1 over cosine x. And when I do the same quotient rule here approach, we get the sine secant x times tangent x. The derivative of cosecant x is going to be minus cosecant x cotangent x. Let's rewrite that. minus cosecant. Keep working on this. Cosecant x cotangent x. And then the last one would be the derivative of cotangent x equaling minus cosecant squared x. So those give us the derivatives of all the trig functions that we have. Now, some of you may say, do I have to memorize all those? Well, you do, but there's a really cool pattern here. And this is something I think that's really nice to see. There's this relationship between these. So first of all, we've got these functions that are called cotangents or cos and things that are not cos. What does co mean? Well, co refers to complement, and that means that complement means that things add up to 90 degrees or pi over 2 radians. So in this case, if I were to have pi over 6, then pi over 3, if I add those together, let me rewrite this here this way. If I have pi over 6 plus pi over 3, those equal pi over 2. So these are complements of each other. And what that means in terms of the trig functions is that the sine of pi over 6, and if I have the cosine of pi over 3, they are complements of it. So cosine is the complement there because it's got the co in front of it, that these are going to be equal. All right. And that works for anything that if you take a trig function and you take its co-part, then it's going to be, if the two angles add up to pi over 2, then they're going to be equal to each other. Just like we have here, the sine of pi over 6 is going to equal the cosine of pi over 3 because one is we have the sine and then we have the cosine, and pi over 6 plus pi over 3 equals pi over 2. That was just a little commercial break. If you've ever wondered where these cos come from. Now, we can use this idea to get a table that represents these trig functions, the derivatives of them. So derivatives of non-co-trig functions, and then we have derivatives of co-trig functions. So what are my non-co ones? So I've got sine, I've got tangent, and I've got secant. None of these have co in front of it. But what are the equivalents then of these? Well, if I take the sine and I put a co in front of it, I get cosine. And if I take tangent, put a co in front of it, I get cotangent. And if I take secant and I put a co in front of it, I get cosecant. All right. And what are these derivatives? Well, the derivative of sine is cosine. And when I do the derivative of cosine, then I'm going to take the co of what we got here for the derivative of sine. We got co. So now I'm going to do the co of that, which would be the co-cosine. But because this idea of co is complement, the co-cosine would just be the sine. All right. So I'm going to get over here for the derivative of cosine, it's going to be sine. But everyone's going to have a negative over here. All right. If I do go back and I do now the derivative of tangent, it's secant x tangent. Oh, sorry, get that right here. It is the derivative of tangent is secant squared x, and the derivative of secant is secant x tangent x. Now, to find the derivatives of the cos there, I'm always going to have a negative for all these. So all of these have negatives, while all of these with the non-co ones are positives. And I'm just going to take the cos of its equivalent. So derivative of tangent is secant. So when I take the derivative of cotangent, I'm going to go cosecant squared x. All right. When I do the derivative of secant is secant tangent. So I get now cosecant x cotangent x. So whatever I had over here, I do cos of it. Whatever's on the left side for the derivative, I take the cos of it, and that's what goes on the right side, and I put a negative in front of it. All right. I think that's really cool. Everything that has a non-co trig function is a positive value for its derivative. And if I memorize those three, then I can find the derivatives of the co-trig functions by putting a negative in front of the equivalent part and taking the co of what I had for the non-co. So again, just, okay, re-harping on this. If I've got cosine here, then I'm going to have minus co-cosine here, which will be minus sine. If I have on the left, if I've got the derivative is secant squared, then over on the right side, I'm going to have negative cosecant squared. And on the left, if I've got secant tangent, then I'm going to have on the right, I'm going to have negative cosecant cotangent. Maybe I've overkilled that, but that's the idea there. Now, and how can you remember the derivative of tangent and secant? All right, there are a couple of ways to do these. You could just come up with some type of memory device to help you this. When I was younger, I always thought the derivative of secant, it seeks itself, so it has a secant and a tangent there. Tangent, the first letter in tangent is T, it's the same first letter in the word two, so that's why we have two secants there. That was really dumb, but I remembered that when I was young. But I think another good way to do this is notice that when I have a derivative tangent is secant times secant. So I've got, in that whole process there, I've got the tangent, and then I've got a secant. So I always have a tangent and two secants. All right, when I take the derivative of secant, I've got the secant, and the derivative of it is secant tangent. Again, I've got two secants and a tangent. It's just the order is different. So derivative, so when I've got the derivative of tangent, I've got secant. So a tangent, a secant, and a secant. Okay, and if I do the derivative of secant, I've got a secant and a tangent. So I've got a secant, and a tangent there. Okay, that might help you remember those different values there. Okay, talk about here. That's now in trying to formal proof that the derivative of sine is cosine. Remember, we did an informal proof, kind of a thinking of it in terms of its graph, but there's a formal proof that you could do, and I mentioned you can find that online, or you can find it in a book, textbook, or whatever. In that, they use two limit properties, and I'm going to just go over these because come up in homework and some problems. I don't think of them as being very important, at least for when I think of trig or I think of calculus. I don't think of them as being the greatly important things, but they're used to prove that these results are there. So they're often presented in this section here because you need to use them to do a formal proof that the derivative of sine equals cosine, and likewise the derivative of cosine equals negative sine. So to this, and prove, okay, let me do this. So I've got these two results here. The derivative of cosine is minus sine. Okay, and in these, we use the two limit results. The one is the limit as x goes to 0 of sine x over x equals 1. And that limit can be proved by using the squeeze theorem. And show that the cosine of x is less than the sine x over x, which is less than 1. And so by squeeze theorem, well, and we also know that limit as x goes to 0 of cosine x is 1, and the limit as x goes to 0 of 1 is 1 because there's no x's there. So by the squeeze theorem, the limit as x goes to 0 sine x over x is 1. Okay, so that you could show that one. This one is the limit as x goes to 0 of cosine x minus 1 over x is going to equal 0. Okay. Notes, I show you how you can prove that one. I'm not going to do that right now. Instead, I'm just going to go over some examples of how these limit properties are used in some of the homework so that you'll be able to do those. Okay. Examples of using these limit laws. So we're going to find the limit as x goes to 0 of the sine of 3x over sine of x. Now, go back to when we think back to limit laws, okay, we'll think, what do? I do a direct substitution, and here, when I put that in there, I get the sine of 0 over the sine of 0. Sine of 0 is 0, so I get 0 over 0, so it's an indeterminate form. So I have to do some type of further manipulation on this. Usually when we did manipulations earlier, that meant we could do something like factor it, or we could add fractions together, or we had a square root. This doesn't have any of those in there. So we can have to come up with a new approach to this. And the new approach is to use that from above, this number one, that the limit as x goes to 0 of sine of x over x equals 1. Okay. We had this from up here. Okay, so how are we going to do that? We're going to rewrite this. The limit, my original problem is this, the sine of 3x over sine of x. Well, this one here, this result, really means, I can think of it this, is the limit x goes to of the sine of box over box equals 1, as long as what's in the box is the same. So I'm going to take what I have in my original problem, and I'm going to break it up into two fractions. I'm going to put the sine of 3x here, and I'm going to put the sine of x here, and I'm going to put some question marks there. All right. So if I multiply those together, assuming whatever I put in the question mark on the top and the bottom, they match out, that's my original part. And now I can think of these things as a box. So here's a box, and I'm going to call this one a triangle. Okay, so what I want down here, I want another box here. I want to have that box there, because then this is going to be the same thing as the sine of box over box, and that's going to equal 1. So I want to have whatever I have in the red box in the top, I want to put that in the bottom. So in other words, I want to have the limit as x goes to 0 of sine and my red box here over my red box, and inside that red box, because on the top I have a 3x, I want to have a 3x here. All right, now on the next one, I have a sine of a triangle. Let's do a triangle in red. I want to put a triangle here. And what do I have in the triangle? I have an x, so I want to put an x here. All right, now that doesn't balance out because I have a triangle over so what I need to do is to balance that out, I need to put the triangle on the bottom and the square on the top. So now I have those balance out, and I have a 3x in the box, and I have an x here. So if I look through this, basically what I've added, this and this cancel out, and this cancel out, and I have what my original part of sine of 3x over sine of x. But I've rewritten it this way because it allows me to use this limit result, number 1. So I have the sine of 3x over 3x times x sine of x, and then I have a 3x over x. And what do I get with that? Well, by the limit law, this one is going to equal 1. This one's going to equal 1, and that may be a little confusing, because you may say, well, wait a minute. We knew the limit as x goes to 0 of sine of x over x equals 1, but about the limit as x goes to 0 of x over sine x. Well, all I've done is I've flipped this. I've inverted it. So if I invert that, I have to invert this. Well, what's the inversion of 1? Well, 1 is 1 over 1. So this could be the same as 1 over 1. So this is just going to be 1 over 1 or 1. So same fact that the limit as x goes to 0 of x over sine x equals 1. Okay, both of those are true. So that's why in this one, which I'll now do in green, there, that equals 1. And the last one in purple here, I've got this. What does that equal? That equals 3. So I get, my final result is that the limit goes to 0 of sine of 3x over 3x times x over sine of x times 3x over x equals 3. All right. So in summary, then, my original problem, the limit x goes to 0 of sine x 3x over x equals 3. That's the result I get. Okay. That's a little confusing. You can rewatch this video. I also have another example with different numbers in the lecture notes, so you can check that out. Let me end by doing one more example here of this, because these can be hard. So then we want to do, find the limit as x goes to 0 of 1 minus secant x over 2x. Now, in the previous one, remember going back up here, circle the previous one in blue here, I had the sine of 3x over the sine of x. And I've got the two limit laws here. I'm going to do these in orange. Okay. Number 1 and number 2. And when I looked at the blue one that I circled, the original problem, the example, find the limit is 3x, sine of 3x over sine x. Which one does that look most like? It looks more like number 1, because I have a sine x over x. Okay. Well, look at this current one, which I'll circle in green here. Okay. Does it look like the first one or the second one? Well, it doesn't look like any of them yet, So we're going to try to rewrite it so that get either sines or cosines, so that if I have something that has a sine in it, I will use that first result in the limit. And if I have something with cosines, I'll get the second one. All right, remember, let's go back to these. The first one there in yellow or orange is the limit as x goes to 0, sine x over x. So I've got a sine there. In the second one, I've got the limit as x goes to 0, cosine x minus 1 over x. I've got cosines. That's a key to determine which one of those to use in my problem, because I want to get my problem I'm looking at, like this one, in terms of sine and cosine. So we're going to rewrite this one. The original part, so the limit as x goes to 0 of 1 minus secant x over 2x. So let's rewrite this. I don't have none of those two limit laws has a secant in it. So let's get rid of the secant. The secant is 1 over cosine. So I'll substitute that in. All right. That still doesn't quite look like one of them that I have yet. So let's get a common, let's simplify the numerator by getting a common denominator. So that common denominator is going to be cosine x. So I'm going to get cosine x over cosine x minus 1 over cosine x all over 2x. So then I can rewrite that as the limit as x goes to 0. Combining those, I get cosine x minus 1 over cosine x all over 2x. Okay. And now at a fraction over a fraction, because the denominator is 2x, but that could be 2x over 1. So I rewrite that as the limit as x goes to 0. I can read that as a multiplication problem by putting cosine x minus 1 over cosine x times the reciprocal of the denominator. So that's 1 over 2x. So just one more little simplification here. I'm going to have cosine x minus 1 over 2x times cosine x. Now, go back to my two limit laws that we have from this chapter, the ones that are circled in orange here, or gold, whatever color that is, I just don't know. I have a sine x in the first one, and a cosine x minus 1 in the second one. Well, this is looking, what I've got here in green here, looks like the cosine one. Remember, the cosine one was the limit as x goes to 0 of, let's see, we got cosine x minus 1, cosine x minus 1 over x equals 0. So there's some similarities there. We've got a cosine x minus 1, I have a cosine x here. Okay, I need an x there. Well, I have an x here. So let's take this, what we have, and break it up into two fractions, just like we did in the previous one. We're going to put a cosine x minus 1, and we're going to put something over here. And what do I want over in the denominator of the first part? I want an x. Why do I want the x? Because then it would match up this. Okay. So if I take a cosine x in the denominator, then what am I left in the denominator? I've got 2 cosine x, right? Because why is that? Because I have this part here. If I take that x out here, then I'm left with, in red, the cosine x and the 2, and that's what goes down here. But what do I have in the numerator? Well, I've taken everything out of the numerator, so I'm just going to have a 1 left there. All right, now what are these limit values? Well, let me rewrite it so it's a little bit clearer. So I've got the limit as x goes to 0, cosine x minus 1 over x times 1 over 2 cosine x. All right, now we do direct substitution, or we can use the limit laws. This limit here is equal to 0 by that limit law number 2 that we had up here in orange, this one right here. That gives me 0. All right, what do I get for the second one? Well, the limit as x goes to 0. If I do direct substitution, I'm going to get, this is going to be the cosine of 0, which is 1. So I'm going to get 1 over 2 times 1, or 1/2 here. And so in essence, then I got 0 times 1/2, which is 0, and that's my answer. All right, hope that helps you understand these derivatives of trig functions. Have a great day.